Good afternoon. That was pretty a good introduction, so I don't really have much to add to that. But so what you can expect today from this talk is really understanding what the modern stream processor or the stateful stream processor really is about, why it came around, and I will also give quite a bit of detail on how Flink and Flink's approach on implementing a stateful stream processor. A little bit about me. I'm a PMC committer at this Apache Flink project. If you follow the project, I've been working on various topics within the project. For example, exactly one streaming connectors or anything state related. For example, evolvability of stateful streaming applications or state backends, which we would actually go through quite a bit today. Software engineer at Ververica, and I work full-time developing open source for Apache Flink, which is part of what I do here, yes. So what we will talk about today is, as I mentioned, what is stateful stream processing and how it has evolved over time, and Apache Flink's take on stateful stream processing. Okay. So first of all, what exactly is stateful stream processing? We have seen over the past years quite a few different frameworks that have came around, starting from Apache Storm. Before I was working on Ververica as an open source maintainer, I was also a data engineer. And at the time, I was maintaining a streaming system which was based on Apache Storm. Now Storm also has some stateful capabilities, but at the time, back at the time, Storm really was, normally people use it as a stateless stream processor where you maintain your state in an external storage to work along with your stateless streaming pipeline. And it was designed that way without stateful stream processing in mind at the time was really because stream processing at that time was really used or seen more as a approximate or real-time layer. So in the so-called Lambda architecture, where you have a real-time layer to generate these in-flight aggregations to show what is the real-time result. But those results are usually just approximate and used as only to complement batch results, which I would go into in a sec. And then came Spark, and then Samza is actually a breaking point here in this history is really because Samza introduced something which I'll be talking about today called stateful stream processing. Stateful stream processing. But this was, in my opinion, more lately made popular by Apache Flink, this project. There's other projects that came after Apache Flink, for example, Apache Apex, Apache Gearpump, these kind of computing, also streaming frameworks. But I'm not saying that they're not as powerful, as good, but it's really just how much of the streaming community is using each project at the moment. So, to really let people understand what stateful stream processing is about, this is an example that I usually give quite a lot. So, nowadays we collect data, and these data are all continuous data. And we collect them in various different kinds of ways. We could collect them in a queue, like Kafka, or we could collect them via a log, any file, which is also some form of collecting continuous data. But how do we actually process these before stateful stream processes actually came around? The usual way we do this is, so what we do is we form time boundaries between these continuous data, which basically means, for example, from 3 p.m. to 4 p.m. this hour, the data that I received, I make it into a batch file, I format it as a batch file, and then I use batch jobs to process these continuously generated batch files, even though the data is continuously generated. Okay? So this is how we, in the past, what we would traditionally do to handle these kind of data. And what these batch jobs generate as results is then served to the end user or end service via another database or whatever to store the results. Now this looks sort of okay, but if we consider a very simple thing we're trying to do is we're trying to compute this conversion metric of each hour we want to compute how many times a conversion of event A to event B has actually occurred. Okay, so we want to compute this. Now using this approach, what we would normally do is, okay, let's say if in the ideal world, A and B happens within always the same time boundary, then things are simple because we don't really need to carry any intermediate state to following batch jobs. But in this case, if A happens in this time boundary, but B happens in the next time boundary, then what you would need to do is the first job's output needs to carry some intermediate state as input to the next batch job, right? And then the second batch job needs to somehow correct the result or output of the first batch job. So there's a lot of moving parts in this approach. And this is where it kind of gets a bit funky, and it gets even more complicated if, let's say, A and B, these two events come out of order, which is completely normal in the real world, right? So why is this, why do we have so many moving parts in this scenario? The thing is, data is continuously generating, and the computation that we're doing has a continuous state that changes as each event comes in. So using a batch scenario to really treat these computations just isn't right? So the ideal way is really we have this queue, we collect these data with whatever way we do it, and then we have one long-running computation, also called streaming computation, which accumulates state. Now, what the state really means is the history of a stream represents is represented by the state. And this state could really be anything. It could be as simple as counters, in-progress windows, window aggregations. If you're familiar with streaming, you would know the term windowing aggregations. Or if you're using this streaming computation to incremental train a machine learning model, for example, the state would basically be the parameters of the currently trained ML model. Okay? Now, the most important thing is that state influences the output. Right? So this is the essence of state within a stateful stream processor. There's another notion of time here that we wouldn't go into detail here, but today. But what this basically means here is that a long-running computation, as it is collecting data, it needs to know when data is complete. When data is complete. For example, in this scenario, when we're trying to compute a result of 3 p.m. to 4 p.m., we need to know, okay, I have completely received all the data that I need for this window, or this time boundary. Okay? So this stream processor needs this notion of time to know when data is complete and when it can generate results. And that is also another hint of why this is generally not correct, because it is hard to also reason about how do you know by 4 p.m. all the events that belong to this bucket or this window has really been received at the server side. So to wrap this part up, it's really stateful stream processing. It's not really about real time. It's not really being about real time, but it's more about a correct paradigm to handle and process continuous data. And being real time is really just a natural consequence of it being a stream processor. So, so much about the concept part of stateful stream processing. Now I'm going to go into Apache Flink's take on stateful stream processing. This is going to cover more about internal details instead of let's say, the Apache Flink programming API. I'm sure the programming API is completely accessible on the Apache Flink documents. So I would say it's going to be a bit of a geeky section, but I hope you all like that. Okay. So just to start this part, what exactly is stream processing? Stream processing is you write some code, and this code is run by the system, executed by the system, which runs 24/7, is a long-running computation. And what it does is basically it takes one record, and then in real time transform it into a new record. So each input stream, the input stream is basically transformed into an output stream. Okay. Now, distributed stream processing is you have this input stream, but you partition it given on some key. Let's say it's a stream of user events, and it is partitioned by user ID. And now each instance of the distributed computation is then responsible of a specific key range of the distributed stream. Okay. Now, what stateful stream processing is in your code, what you would feel like is you're basically maintaining some local variables, but what these local variables is really accumulating state of what the previous events in the stream has shown so far. And then based on the state, you manipulate, influence your output. So this is called stateful stream processing. Okay. Now, back in the old times of how we usually handle stateful stream processing is is it can be basically captured by this image here. So you have a Kafka queue, and then you have sources, sinks, and sinks goes to, let's say, a KV store or a cache. And if your computation is stateful, you would store the state in this external state store. Now, why is this hard to maintain? This is hard to maintain basically from two observations you can actually see in this image. One here is this offset. This offset, if you're familiar with Kafka, this offset basically represents the progress in your input queue, how far you have reached in this streaming application. And then each record that is consumed will affect what state is represented here, right? It is hard to really keep a consistent view of this offset store and this external state store and what is produced to this KV store, because everything is not handled to be consistent by the stateful stream processor, but the user of this stream processor needs to handle this consistency here. So Flink's approach to stateful stream processing is really internal state. Internal state. So the things mentioned here about external state was basically what I mentioned. It's usually much slower due to remote read and writes against that external state store. You could say that fault tolerance and scalability is left to that external storage. But then the disadvantage is really this remote read, which would more or less become this performance bottleneck sooner or later once your business scales. Okay, and it's not that easy to get this exactly once guarantee, which is crucial for if you want this pipeline to be really producing accurate results, which you would be relying on your business. Okay, so internal state. What this really means is, okay, each computation instance has some notion of a local state backend. And each state read and write, each state access really goes to this local state backend. And what this stream processor needs to do is really handle fault tolerance of this local state, right? And this is really handled by, in Flink terms, it is periodically snapshotted to this stable storage. And this stable storage is basically a distributed file system. It can be HDFS, it can be S3, it can be zeros, it can be any file system or somewhat similar solution in the cloud, some cloud providers right now have. Or it could be just any network-mounted file system. Anything that is accessible throughout all the computation, all the nodes, can serve as this stable storage. Okay, so far so good. Internal state, we have local reads and writes. Performance-wise, it is superior to external state. But the stateful stream processor then needs to handle the process of periodic snapshotting and restoring and maintaining basically fault tolerance of the state. So how does Flink actually do that? We can first consider a very simple case of how to do this. Let's just consider the simple case of just one process. There's no distributed environment, but just one process consuming one queue of events. What we can do, and here it says local state, but it can just be anything. It could be just a process and some in-memory data structure in this process which has some values which represents the state of this computation. So what is basically done is, for each record, what you can do is, when you process each record, you take a snapshot. And this snapshot includes two things. The first thing is the value of that state variable, right, or whatever is in the in-memory data structure of this process. Take a snapshot of that, as well as the position in the queue that it has processed. So each state value corresponds to a position in the queue. Now, as you process further records, if let's say you process to this record, and now the process fails for any reason, all you have to do is find the last snapshot. Let's say this snapshot represents position here, and at that point in time, the state value was some value. Now, so it's really just replaying that process and then resetting the position of the queue, and then starting to replay from there. Using this scenario, in this very simple case, then you can actually achieve exactly once guarantee. But the interesting question is, how do we create consistent snapshots of distributed embedded state, right? Or more importantly, how do we do it efficiently without abrupting computation? In the distributed scenario, we also have this queue. And we have this queue, and when we have distributed operators of streaming pipeline, that is basically all records are pipelined through all the operators in this DAG. Okay. Okay, so what is done here? As records are pipelined through, the consistent view of a snapshot, similar to the single process scenario, is we also need to have a position in the queue, but the state corresponds to all the local states of each operator. Okay, so this is the consistent snapshot. Now, fairly straightforward. So if some code, some operator fails, all we need to do is we periodically checkpoints all these local states along with their position offset into the file system, and if anyone fails, then we just restore everyone. Reroll is basically like a reroll operation, similar to the simple case. But the question is, how do we do this efficiently? The dumb way to do this, or the simple way to do this, is really just say, okay, for each record consumed from, let's say, Kafka, it has to traverse through the whole DAG before I can let the second record, the next record, go through, be pipelined through the DAG. Now that's not good because we're basically doing a global stop on the computation for earlier operators to actually generate this consistent snapshot, so that's not good. So in Flink, how this is done is it's called a mechanical distributed snapshots. And if you're familiar with in-memory databases or come from a database area, this is basically a variant of the Shandy-Lamport algorithm. So in Flink, this is called a synchronous checkpoint barrier. So what is essentially done is Flink will inject these special checkpoint barrier events to be pipelined along with the events. And the checkpoint barriers cannot override, or the ordering cannot change as soon as they're injected. Okay, let's see how this is actually used in the framework. So this is really used by let's say we have a job here, 2 Kafka partitions, and we have 2 sources and 2 operators which have local state here. Now, let's say Flink says we need to inject a checkpoint barrier. We need to take a snapshot of the distributed pipeline right now. What happens is this checkpoint barrier is injected, and then it flows along with the following events into this next operator. Now, by the time this checkpoint barrier has arrived at this operator, all the events that were after this checkpoint barrier has been manipulated into the state, right? It has been processed and it has changed the state. So the state corresponds to that position in the checkpoint queue. And what this really does, once the operator receives this checkpoint barrier, what it does is it triggers a state snapshot. Now this is really just a very small synchronous part where it does a copy on write operation. What this copy on write operation really does is so that the copy of that state can be asynchronously transmitted to the central DFS for persistence, but at the same time, during this transmitting, which is asynchronous, processing can continue and to manipulate the state without this state of that previous checkpoint being transmitted to be corrupted. Okay. So that copy and write operation is just so that the synchronous part of this snapshotting is very, very small. It's very, very lightweight. The heavy part, which is actually the transmitting, is asynchronous and does not stop the processing. Okay. So this is really how Flink, and there can be multiple parallel checkpoints that are happening throughout the pipeline. I was just showing a procedure of one specific checkpoint happening. Cool. This is even a bit more detail about how this checkpoint aligns. Let's skip this part because we actually don't have too much time for this. Okay, so I just want to quickly show the synchronous checkpointing part. So the synchronous checkpointing is really just, this image is really just showing the difference between synchronous checkpointing and asynchronous checkpointing. If we don't have asynchronous checkpointing implemented, then when the checkpoint barrier arrives at the operator, it basically uses the same event processing thread. But the event processing thread is blocked to, and this red part here is really the part which is the time taken to transmit to the DFS. But with asynchronous checkpointing, here, this snapshotting part really is just fairly small, and as soon as the synchronous part is ended, then it just starts continue with this event processing and leaving the checkpoint thread to do the transmission to the DFS. And this is all based on copy and write. It's basically an implementation of MVCC. if you want to check that out. Okay, so up to now, it's really only about how Flink snapshots take these consistent snapshots consistently and efficiently. Now it's about how does Flink handle large state. So your state can be arbitrarily large. Users have been reporting gigabytes or even terabyte levels of state within production jobs in companies like Netflix, Uber, Lyft, and even some users which that I just recently learned about in the Southeast Asia region. For example, Gojek and Grab are also all using Flink in their production pipelines at the moment. So how do we handle very large state, which goes beyond the memory size? So really, state access in Flink, as I mentioned, your code would really look like something like this, where you access the state, each read and write goes through an actual local state backend. Okay. Flink right now has two flavors of state backends. By default, you would use the Heap backend, which all state lives in memory on Java Heap, and read-write basically operates on Java objects, and state size is essentially bounded by the memory size or heap size. The other flavor, in case your state is arbitrarily large, which is mostly used for production, is RocksDB backend, where your state actually lives in off-heap on disk. By the way, the user doesn't really see the difference. It's really, the user API just feels like accessing a local variable, but it's just going through these different flavors of backends. Operates on BICE, uses serialization. So one performance hit already is this serialization here. So even though the RocksDB backend can handle larger state sizes, but the disadvantage is really if this serialization overhead would affect the throughput. So I think benchmarking-wise, it's a 10 times difference, but it comes with different state size capacities, of course. So just a very recap, the Heap backend, the way I like to say it is lazy serialization and eager deserialization, as what it means is on every state access for per record, you would not go through any Java serialization, any serialization, sorry. It's really just Java object manipulation. But when you actually receive the checkpoint barrier and want to persist that to the DFS, when the system persists each local state to the DFS, then serialization happens. And when you restore from the DFS, then you eagerly deserialize, as in you deserialize everything into objects already at restore time. Okay. For RocksDB, it's the other way around. Eager serialization, lazy deserialization. So on per record, what happens is you need to go through a deserialization round trip on each record's computation. And then on checkpointing or restore, what really only happens is you could just think of it as a dump or an exchange of state byte blobs. Okay. And another part about how Flink handles large state is something we call incremental checkpoints. So to understand this is an image, this is a demonstration of full checkpoints. So what happens in full checkpoints is, let's say you have checkpoints at T1, T2, and T3, and the state is ABCD at T1, at T2 it is AFCDE, whatever, and T3 there's also another form. But on each checkpoint, the whole complete state is checkpointed. Now, if your production job really has the state sizes, as I mentioned, 50 gigabytes or terabytes levels, this would be a problem, right? So we were talking, the community, Apache Flink community was talking with companies like Netflix, Uber, and then we came up with this incremental checkpoint concept, which is actually fairly straightforward to understand. So we have ABCD at T1. At T2, it's just that the red key has changed to a value F, a different value, or we have a new key E here. So what we want to do is for the checkpoint 1, it could be the full snapshot, but for following checkpoints, it's really just the delta, the difference in what has changed in the state. And this dramatically reduces the state size that needs to be transferred to the DFS for each checkpoint, right? And it also depends on your use case and state access pattern, but in most scenarios, this works quite well. Right now, as I mentioned, there's two different flavors of state backends in Flink right now. There's Heap and there's RocksDB. Incremental checkpoint is only implemented in RocksDB. I can explain why here. RocksDB, or let's say to be more accurate, LSM trees is naturally well suited for implementing incremental checkpoints. Saying RocksDB here isn't that accurate, but in general, LSM trees. If you're familiar with the data structure LSM trees that RocksDB or LevelDB uses within their databases, it's somewhat like this. So all your writes goes into this in-memory index, which is generally called a mem table. And once this mem table reaches a certain size threshold, the content of the mem table is dumped into an SS table. And this SS table is really just, you can think of it as a sorted file, sorted index, which is sorted by key. So once every new SS table is generated, these SS tables are continuously merged into lower level SS tables. And this merge can be done quite efficiently because every SS table file is sorted by key. So when you merge, it's really just a merge sort operation. So the essence here of why this is suitable for incremental checkpoints is that because SS tables are immutable. So our SS tables, as SS tables are generated or deleted because of compaction of LSM trees, the difference of created and deleted SS table files basically essentially captures the delta of state here. Okay, so Flink basically uses this behavior to capture incremental checkpoints. Now, for Heap backend, it is also similar. It is also possible to implement incremental checkpoints because the data structures in the Heap backend already support MVCC. So it is somewhat possible to implement incremental checkpoints and detection of the delta of state there, but since Heap backends are generally used for small state sizes, having incremental checkpoints supported there isn't really a higher priority of the community at the moment. So that's why only RocksDB implements incremental checkpoints right now. Okay, for the last part, I want to quickly talk about Queryable State. It's not really a production-ready feature yet in Flink, but we're working towards it. But I want to quickly explain why it is actually quite an exciting feature. So if you haven't noticed already by now, the state within Flink is essentially a key partition sharded KV store, right? Because you partition your stream, so the same key always goes to the same computation instance, and at that computation instance, the state for that key is always locally accumulated there. So you're basically also partitioning this generated state by that key. And let's say you have a window operator generating results per hour. This state here within that window operator basically represents the in-flight aggregations, right? So let's say your scenario right now is you're trying to generate a dashboard which shows the historic aggregations of each hour in the past, but at the very last column, what it is showing is the in-flight aggregation of a current minute or whatever, of a current minute, a real-time view, basically. In the past, we would have this Lambda architecture, which would have the streaming layer and then the batch layer. It would have a lot of moving parts to actually just to be able to generate such a view. But using the Stateful stream processor and so-called this Queryable State feature, it can be actually very straightforward. So you have this window operator, which is generating the hourly aggregates and then storing them into the KV store. But if you want the real-time hot data, hot result, what you basically need to do is just query a state within this operator to know what is the real-time in-flight aggregation. Okay. So using this query service, which basically delegates this this query to the KV store or to the in-flight state within Flink, this can serve that dashboard we were talking about just now. Okay. I have a whole other section for outlooks for application architectures. So that was about stateful stream processing Flink and the current state of things right now. But I also have quite an opinion about how the stateful stream processor would fit in microservices or application architectures, which I would love to talk about if you are interested in. And I also have an office hour at 3:30, I think. So if you're interested, feel free to come approach and we can discuss it. That's all for today. Thank you.